This time I want to show you how to calculate the 1 dB bandwidth, or the 10 dB bandwidth, or the 15 dB bandwidth, or the 6 dB bandwidth from the 3 dB bandwidth. This method works for any circuit in which you can express the gain in terms of a low frequency gain, which I'm writing as GDC, the gain at DC, divided by 1 plus J F over FB, where FB is the break frequency, or in other words, the 3 dB frequency. And that's the gain as a function of frequency. So this would apply to op-amps, as well as applying to the simple resistor-capacitor circuit that we've looked at previously. Now I should point out again that FB, strictly speaking, is not the 3 dB bandwidth. It's the frequency at which the gain has dropped by a factor of 1 over root 2, which is not exactly 3 dB, but it's very close. And that's because if I take the modulus of this denominator here, what I get is GDC over the square root of 1 plus F over FB all squared. And when F is equal to FB, that just becomes 1 plus 1 squared, or 2, so this becomes the square root of 2, it's GDC over the square root of 2. Or writing that down so you don't have to remember all of it, G of FB would just be G of DC divided by the square root of 1 plus FB over FB is 1 squared, and that's just equal to GDC over the square root of 2. So strictly speaking, FB is the frequency at which the gain has dropped from GDC to GDC over root 2. And expressing that in terms of dB gives 20 times the log of the square root of 2, which is not exactly 3, but it's so close that we tend not to worry about the difference. But there is a slight difference there, and if you do come across a calculation in which there is a slight difference between the 3 dB bandwidth and what you were expecting it to be from this expression, then that's probably the cause. Anyway, let's move on. Supposing I don't want the 3 dB bandwidth, I want the X dB bandwidth. Well, the X dB bandwidth is the frequency at which the gain has dropped by X dBs. In other words, it's the frequency at which the gain is GDC divided by 10 to the power of X over 20, because that is a factor of X dBs expressed just as a voltage ratio. This whole term, in other words, is X dBs below the gain at low frequencies. So if I want to know at what frequency the gain has this value, I just equate this to this expression here, which is the gain at the frequency F. And I can see that these expressions are going to be equal if the square root of 1 plus F over FB all squared is equal to 10 to the power of X over 20. Squaring both sides and subtracting 1 would then give me F over FB all squared equals, well, 10 to the power of X over 20 squared is 10 to the power of X over 10. And then if I subtract 1 from this side, I will get this. Take the square root of both sides and multiply up by FB, and I get F is equal to FB times the square root of 10 to the power of X over 10 minus 1. And this is my X dB bandwidth. I'll call it F X dB, the frequency at which the gain has dropped by X dBs from its low frequency value. So for example, the 10 dB bandwidth would occur when x is 10, that would be FB, the 3 dB, times the square root of 10 to the power of 10 over 10 is 1, so that would be 10 to the power of 1, or just 10, minus 1. The square root of 10 minus 1 is 3, so that would be 3 times FB. That's the 10 dB bandwidth, the frequency at which the gain has dropped by 10 dB from its low frequency value. If we try to work out the 3 dB bandwidth, then what happens is this. FB times the square root of 10 to the power of 3 over 10 minus 1. And that is 0.9976. So, the 3 dB bandwidth is 0.9976 times FB. Just a reminder, I do keep referring to FB as the 3 dB bandwidth, but that is just a common approximation. FB is actually the frequency at which the gain drops by a factor of 1 over root 2. It just so happens that that is very close to 3 dBs. As a quick example, let's look at this problem. What's the 10 dB bandwidth of this amplifier? Well, first thing to note is that this is a summing amplifier. And the formula for the 3 dB bandwidth of a summing amplifier is the gain bandwidth product, in this case 2 MHz, divided by 1 plus the sum of the modulus of the gains. Both gains in this case are 2, or minus 2, so the sum of the modulus of the gains would be 2 plus 2, or 4. So the 3 dB bandwidth of this amplifier, FB, would be 2 MHz divided by 5, which is 400 kHz. We know from this formula that the 10 dB bandwidth is 3 times the 3 dB bandwidth. And therefore, the 10 dB bandwidth of this circuit would be 1.2 MHz. 3 times 400 kHz. If in any doubt, we can always check these things in the simulator. I calculated the 10 dB bandwidth as 1.2 MHz, so let's just set the frequency straight to 1.2 MHz and see what the output is. We would be expecting it to be 10 dBs below 4 volts, so that would be 4 times 10 to the power of minus 10 over 20. That's 10 dBs below 4 volts, or 1.265 volts. And at 1.2 megahertz, it is spot on, 1.265 volts. And this one, of course, is precise, because we haven't had to make the approximation that 10 to the power of minus 0.3 is around about 1 over root 2. At 3 times FB, the gain really has dropped by 10 dB. That's all I want to say about the bandwidth of op-amp amplifier circuits for now. There is plenty of practice available on the quiz app.